Hello everyone. Have you ever wondered how applications like Google, Facebook, Meta, they are being built? So, my name is James. I'm a computer science graduate turned teacher, and in this video, I'm going to answer how software is being developed, which is part of the A-level computer science syllabus. And before I begin, I would like to ask you for a favor. And if you like my video and if you think that I have helped you a ton, do consider hitting the subscribe button. And let's aim to have 30% of you subscribe by the end of next month. Thank you so much, and this will be the only favor I ask from you. Now, let's dive into what we will be learning today. So we'll first look at how software is developed through this cycle and look at some of the tools that software engineers use, followed by errors, testing methods, and strategies. And we'll end the video by the different types of maintenance someone can do to the software. Now, let's look into the program development life cycle. So this is the cycle that almost every company use. They might not name it this way, but this is the gist of it. The first step before you started coding on building the application, you will need to do some analysis on what the requirement specification is. So I have a definition here, but what it's saying is that you need to figure out what is the problem that your application is trying to solve, or what is the convenience that it will provide. And when you're planning a solution to reach your requirement specification, there are two different approaches. A bottom-up approach, meaning you build from individual components to create a whole system, like a Lego. Whereas a top-down approach is by starting at this overview. And after the analysis phase, after you have decided what's the requirement specification and what approach you're going to use, you're going to plan out the algorithm to solve the problem. As learned in the previous chapter, we can plan the algorithm using a flowchart or pseudocode. And that's everything that you do before you even start coding. And next one, which is when we started coding, choose a programming language. Pick one that is the most suitable for the solution you propose. So, like the language we learn in language lesson, programming languages, different types of them, they do different things. So this is when you pick the most suitable one for your application. So you might encounter bugs, but that is when debugging comes in. Check at the end when the code does what it intends to do. So after you launch your software, before you launch your software, that should be when you test out whether it reaches your program requirement or not. And we will explore a few testing methods during the video as well. So this is the life cycle. The reason why it's called a cycle, if you look here, is because every time you implement a new feature, you have to go through the analysis phase again. This is also why every application that you download on your phone, they require software update, because the software developers, after an analysis phase, they figure that, oh, maybe I should add this feature. So this is why they do this all over again to implement the new feature in the application. So that's the cycle part of it. And I want you to teach you about a few software development models: waterfall, iterative, and rapid application development. So let's look into one of them one by one. The waterfall model is a linear and sequential software development approach, linear and sequential, where progress flows downwards through distinct phases, each dependent on the completion of previous phase. So this is how waterfall model look like. You can't do design before analysis, and you can't do coding before design, because each stage relies on the previous stage. So arrow down means the result from one stage are input to the next stage, and more work is required at an earlier stage to complete the current stage, meaning you go back up because there's something that has not been done yet. Now, for waterfall model, I would describe it as a very rigid model, because once you start it, you just can't go back. You can't go from testing all the way back to analysis, because it assumes that all the requirements have been figured out, and then you just follow this progress to create the software. But then it does have some advantages. Stages are processed and completed one at a time, so there's no confusion on what stage we are in. Works well for smaller projects where requirements are well understood. and it's simple to understand as the stages are clearly defined. Whereas the disadvantage is that you are not creating anything throughout this entire process here, because the product will only be shipped after the testing phase. And it's a poor model for long and ongoing projects because requirement might change, which is the third disadvantage. Cannot accommodate changing requirement, which means that if when you're in this coding phase already, you can't add more features because otherwise you have to go 2 level back up. So this is not a good model for a big project. This is what it says here. And an alternative to waterfall model is what we call the iterative model. It is a software development approach that cycles through repeated phases, allowing for flexible adjustment and improvement throughout the development process. So how it works is that instead of figuring out everything about the software, the programmer will start with the implementation of a small subset of program requirement, meaning we create a smaller version of the software first, and then they only go through this analysis, design, coding, testing cycle many different times to add more features at a time. So instead of going all the way from the bottom to the top, they go through this cycle, adding one feature at a time. So the advantage is that at an initial phase of development, a functional system prototype exists, meaning you are creating a real product that the user or the tester can use. Enable easier detection of functional or design flaw, leading to swift corrective actions. So this is important, and there's a principle in software engineering called fail fast, which means that you want to identify the errors in your code as fast as possible. Iterative model allows you to do that because you are creating only a very small software, whereas the waterfall one, when the error is detected, is usually a little bit too late. It's cost-effective in altering scope and requirements, continuous delivery of operational products with each increment, facilitating customer evaluation by feedback by producing software early in the cycle. So what it means here is that the software developer launch a small version of the software to the clients, to the consumer, and allow them to use it and test it. So this is important because customers will give you feedback. And when they give you feedback, you can bring the feedback to the analysis, design, coding, testing phase to suit their feedback. So this is one of the advantages of the iterative model. Whereas another one, early in the life cycle, certain functional aspects can be rapidly developed and made operational. Simple testing and debugging if the program is smaller, it's easier to test. Leveraging lessons from each increment for subsequent ones, identifying and resolving risks iteratively. So this is likely the model that you will follow when you are creating an application in the future. Whereas the disadvantage, it's hard to be used in developing small software system because if for a software system, it's already small. So it would be better to use a waterfall model. And potential need for increased resources, design challenges stemming from incomplete initial requirement gathering, difficulty in defining increments, possibly requiring a full system of definition. Disadvantage could be what they're saying is that it could be very vague to the programmer on what you are actually wanting to create. So because it requires consumers' feedback. And that's iterative model. The next one is very similar to iterative model. It is called rapid application development model. It's an approach emphasizing quick prototyping, meaning you create a real product, an iteration cycle for rapid system development. The advantages: accessible progress, enhanced productivity, prompt initial assessment, diminished development duration, stimulate customer input, early integration, resolve integration complexity. So very similar to iterative model, but this one they create a real model as fast as they can, a prototype. So disadvantage, only system that can be modularized, meaning that can be broken down into modules, can be built using RAD, applicability to component-based and scalable system, suitable for project requiring shorter development times. User involvement is required. You need to find a group of people to test your code. Requires highly skilled developers and designers. Now, that's all about the different software development models. So now I want to teach you about the different tools that programmers use. First one is called a structured chart. It is a visual representation outlining the hierarchical structure and relationship between modules. Remember, when we are coding in Python, modules are the functions that we create or the procedure in pseudocode in a software system. So I want to show you an example of a structured chart. For example, I have a program called that will calculate the sum of two numbers. Look, what happened is that you first need to create a module that asks the user for two numbers, followed by a module that calculates sum and outputs sum. So here are some terminologies. This is called module, and parameters are what is being given to the module and what is being output by the module. So if you look at the arrow into the module here, these are the inputs that we are giving into the module calculate sum, and the arrow outside going out from the module is what the module produce, return, output. So sum is being returned to the main module and being input again to this module to be outputted. So this is just one example. Second example, I created this program called which checks whether a customer is eligible for discount. So basically, the first step is to initialize minimum amount for discount, and once the module initializes the value, it return it to the main module, and then call another module input user purchase amount, meaning how much has the user spent, and again this value is being output back to the main module, and the two values here, they are being input into this module called output message, and we have this diamond here, which is very similar to the flowchart diagram that we learned, meaning it has two possible paths. So look, I put a condition here. If user purchase amount is greater than minimum amount for discount, then I will output you got a discount. Otherwise, it will output no discount, sorry. So again, this is just example for you to know how to draw a structured chart. Remember the arrow into and out to output from the module. And that's another one that requires iteration, which is called an n-square generator. Basically, we ask the user for a value n, we square it, and then we increment the count, and then we'll output the n square value. So this requirement says we should output from 1 square to n square. This is why I put an arrow here to signify that every process here will run until count greater than n. Think of it like a for loop that we learn in pseudocode. Okay, so there are two different arrows here. First one is that this arrow, this one is a little bit special. It has two ways, and in the middle of it is an empty box, empty circle. This means that the value is updated within the module. Okay, so I'm sending count into it, and then count is being updated and returned to the main module. Whereas the other one is not in this diagram. It shows that value transferred is a flag, meaning is a true or false value. And that's structured chart. Let's look into another tool that programmers might use to clarify their thought, called finite state machine. So in a computer system, this finite state machine is a computational model characterized by a set of states and transition between these states based on inputs and define outputs associated with each state transition, meaning we want to investigate what causes one state to change to another state and whether the transition will produce an output or not. And to do this, we need to look into two different types of state transition tools. One is the table, one is the diagram. And I want to show you an example of how we could draw the state transition diagram, which I think is something you need to do. So I have a table here that shows that, so this is my state 1 and state 2, and then what state will it go to when an input is being given. For example, the first one, when S1 is given, when the program is in state number 1 and an input of A is given, it will stay at state number 1. And how we draw this in the state transition diagram, first you represent the state with a circle, and of course you start first, and then the input with the arrow. Look, because the input A will cause state 1 to go back to itself, this is why I draw it as such. So let's look into another one. When state 1 is given an input B, it will go to state 2. So this is reflected in the diagram here, as in I draw another state called state 2. And when S1 is given an input of B, it will go to state 2. Now, similarly, when S2 is given an input B, look, instead of going back to S1, it's going back to itself. So I draw an arrow relating S2 go back to itself, but the input is B. And then when S2 is given an input of A, it go back to S1. So this is how we can create a state transition diagram all the way from a state transition table. And if the FSM has a final state, meaning after it goes back here, it stops, this is when we draw a double circle state. Okay, so that's some terminology. And if the transition produce an output, which I'll show you in another example, then we use a straight vertical bar followed by whatever stuff that the program will output when given an input of A, for example. So I want to show you an example of how to draw a state transition diagram for a real life scenario. And in this case, we're going to look into an elevator control system. The elevator operates in 4 distinct states. These are the different states. And state transition occur based on specific criteria. I believe that if you have been in an elevator, you know what I'm talking about. So from idle on ground floor to moving up, or moving down upon receiving corresponding directive commands. So it's a little bit difficult to read the requirement like that. So this is why I simplified for you. First of all, we identify what are the different states in this elevator software. The 4 states, followed by each transition requirement one by one. So what you need to do is that based on this scenario here, you need to learn how to create a state transition table. So I have my initial state column, and what happened that will cause this initial state to move on to the next stage. First question, from idle on ground to moving up upon receiving. So meaning when you are on the ground floor, when up button is pressed, then the next state will be the lift moving up. Similarly goes to moving down. So the next one is that from moving up to moving down to stop at the floor when reaching a floor. So let's say you are moving up, moving down. The condition for you to stop at the floor is when you reach a floor. So that's another state. And the last bullet point, stop at the floor to either moving up, moving down, or idle. So when you stop and the up button, down button is pressed, it will go up or down. Or if it is idle for 2 minutes, then the elevator will just go to the ground floor. And this is the state transition table that we come up with based on the conditions. It's not so hard to draw. But then the harder part might be that you want to create a state transition diagram. But then it's still not very hard. And let's try to solve it one by one. So first we start off with the idle on ground floor circle state. And when up button is pressed, looking at the table, you know that it will go to the moving up state. And when the down button is pressed, it will go to the moving down state. And that's pretty easy. And from moving up to moving down, it will reach the state stop at the floor when it reaches the floor. So this is when you see that moving up and moving down, when they reach a floor, they will go to this state called stop at the floor. And when you are at the stop or the floor state, and the up button is pressed, you will go to the moving up state, and down button is pressed, moving down state. When it's idle for 2 minutes, go to the idle on ground floor state. So by using this table here, we can draw out the state transition diagram pretty easily. And that's just another second example. The last example I want to give you is one that requires the program to output when they transition from one state to another. And I believe this is in your textbook as well. Design a state transition diagram for a 2-complement SSM. It has been designed that will take input a positive binary integer, 1 bit at a time, starting with the least significant bit. The FSM then converts the binary integer into 2-complement negative equivalent. So what does the question even mean? So I've shown this is what it means. Basically, you take a binary equivalent of a positive integer, then convert it into a 2-complement negative number. And the process that it goes through this, remember we're starting from the least significant bit, is that we will output the bits inputs up to and including the first one, meaning whatever the user input, will output it until it reaches the first one. We'll still output the first one, but then after that, we'll output the other bits following this scheme. For each one, output a 0. For each 0, output a 1. And it could be very hard to understand, so let's do an example directly. The input I have is 0, 1, 0, 1, 0, 0. If you convert it to denary, it will be 20. So the goal is that I want to convert this 20 into negative 20 in 2's complement using this scheme. Using the algorithm, whatever the user input, 0, I'm going to output it 0. Until the first one, I'm still going to output it. But that tells me that, oh, after the first one, I'm going to follow the other scheme. So for each one, output is 0. So input is 0 and output is 1. For each 0, so output a 1. 1, you output 0. 0, you output 1. And if you were to calculate it using 2's complement method, you'll find out that, hey, using this algorithm, I already got negative 20 in 2 complement. So this is the method, of course, to explain what the question actually means. But our goal is that we want to draw a state transition diagram. So to do that, we first need to draw the state transition table. So S1 is the state where you output whatever the user input. And state 2 is when you output inversely what the user input. So I want to show you in this diagram, it will be a lot clearer. So at the beginning of the program, if the user entered 0, it's going to go back to yourself, because this state says that you will output 0 when the user output 0. Until the user entered the first one, this is when the program goes from state 1 to state number 2. So if you enter 1, output 1 first. And in state 2, whatever the user input, then you output whatever the inverse of the binary number until the end of the program. And hopefully these 3 examples give you an idea on how to draw state transition table and also state transition diagram. Now, another aspect of software development is that errors could occur. And in this subchapter, we're going to look into why error occurs and what are the different types of error that could appear. So I have a few reasons why error could occur: improper syntax, implementing feature that do not align with what the program requirement says, flaws in architecture, confusing or unintuitive interface, meaning the user don't know how to use it, malfunctioning hardware component. So these are the description. Feel free to read it yourself. Now, testing is a process that we use to find out all the errors in the program. All right, as implied by its name. There are a few errors that I want to go through. First one is syntax error. So it occurs in programming when the code violates the language rules or grammar. So for example, in English, we can't just use "we is a good man." So that would be wrong, right? This is programming language also have the same rules. So if the programmers made this error, then it will prevent proper interpretation or execution by the compiler interpreter. And this is how compiler interpreter handle syntax error differently. So if a program compiles without error, it indicates the absence of syntax error in the code. Whereas for interpreter, syntax checking occurs only on statements scheduled for execution. Hence, on an insufficiently tested program might still contain undetected syntax error, meaning it only runs the code that is in that particular file, whereas compiler runs everything so that it can detect errors better. So another type of error is not so easily to detect. It's called logic error. You'll probably face a lot of this problem when you are coding. It refers to a flaw in the code's algorithm or logic, causing unexpected or incorrect output. So if you look at this code here, Python code, it will look correct until you run the code. You find out that, hey, the program doesn't do what it's intended to do, which is it doesn't find out the maximum. Because if you run this code, it will still print 0. Of course, if you know Python, you will know that the reason is because max number here is being set to 0. So this is why when you put negative number to it, the algorithm will not detect that, oh, this is an error. All right. So this is called logic error, meaning the logic is wrong. Therefore, the program cannot do what it's intended to do. Another one is runtime error. It occurs during program execution due to unforeseen conditions, causing the program to terminate abnormally, or it doesn't terminate at all. Uh, if you know Python, again, this is a code that I written that will never stop forever because I use a while true loop, meaning the condition will always be true. And don't try to put this code into your Python, it will crash. So this is called runtime error, the error that happens only when you run it. Now, we have talked about the different types of errors. Now let's talk about what are the different types of methods we can test out whether a program has error. First one is called stub testing. It involves creating minimal code pieces that mimic functionalities of larger module or components. So there are times when your program is very big, but then you're not at the final stage yet. Yet you want to test out whether it works properly with the module you created. So this is when you create something like called a stub code. If you look at all these functions here, they actually don't do anything. They are just printing. So this is just to complete, for the sake of completing the whole program. Okay, and then what happened after everything works is that the programmer will go to each function and implement the functionality one by one. But then stub testing is a good way for you to see the big picture of the program, how you want to structure it, and it will really make your coding life better. So the second type of testing is called black box testing. So it's a software testing method where the internal workings or structure of the system under test are not known, like a black box here, meaning when the user tests the software, they don't know what the code is like. Meaning that when they test out the software, they only focus on system inputs, outputs, and functionality to evaluate its behavior against specification or requirements. So during black box testing, this is what they will do. They will evaluate the software functionality by providing test data based on program specification without having access to the internal code, meaning they can't change the code to solve their problem. All they do is that I give you this input and whether this program can produce the output that is intended. And that is called black box testing. So the type of data the tester will use, they will first use normal data to validate standard functioning, and then they will use extreme and boundary data to assess system behaviors at limit, to test its limit, and erroneous data to evaluate how the system handles incorrect or unexpected inputs. So that's a black box testing. The user doesn't know what's happening inside the software, whereas white box testing, it is very clear to the user. It's a software testing technique where the internal structure, design, and implementation details of the system under test are known to the tester, allowing the examination of validation of internal code part and logic. This is usually done by the software developers. So for example, the following function will find the maximum number in the list. To make sure that it does its job correctly, we need to test the program using different sets of inputs. So this function, find the maximum value, and to test whether it works correctly, you just try it out with different types of input, like a list that has all the positive number, a list that has all the negative number, and a list that has no number. And you want to see how your code will react when given different inputs. Now, the next one is interesting. Dry running an algorithm, meaning once you have written the code, you pretend that you are the computer and run the algorithm step by step, which is what I just talked about. And one tool that you need is called the trace table to dry run your algorithm. Let me show you. Let's say this is our pseudocode. And what it does is that it takes input from the user and calculate the average of it. In a trace table, how it looks like is that it will have one column, assign one column to each variable that you create. So if you look at here, the first line of code, running total is the first variable. I assign a 0 to it. So what happened is that trace table will trace the value of that particular variable at a particular step. So let's go through the code line by line. First line, for counter 1 to 5. So initially counter is initialized as 1. And next number, by the way, this is our inputs. The first one that we're going to input into the program, 1, 4. And the next line of code, running total equal to running total plus next number. Alright? So you can see that 0 plus 4, which is equal to 4. So I'm actually updating the running total variable here. So because it's a loop, they will continue to run it. next number to which is 5, and the counter has been incremented to 2, and then the running total will be 9 because 4 plus 5 equal to 9. So we keep running the code and then track down what the variable value is until we reaches the end of the for loop. You can see that running total is now 113, and then we'll output. So in the output column here, following this guy, I will output whatever that is inside the running total. And the average will also be calculated by having running total divided by 5, 22.6, at the end of the program output average. So this is what trace table do. It mimic the program and then just run the program one by one to see one line at a time to see how the variable value changed throughout the program. And it will be useful when you are debugging. Let's say your program doesn't do what it intends to do. By drawing a trace table, you know what went wrong. Okay, so that's trace table, dry running an algorithm. The next way we can test a program, integration testing. It is the process of testing combined modules or components to ensure they work together as expected. So in Python, we learn how to write function one by one. Think of integration testing as that when what happens when you combine all the functions that you have written. Does it still work properly? And for bigger software, it could be that when they combine the front end and back end development, the code for that. So incremental integration testing involves gradually integrating and testing new module. So this is another method, incremental integration testing, meaning we add one module at a time to the whole program and then run it, add another module, run it, and we see what is if let's say an error occurred, we can identify which module is causing the error, and then we can focus on fixing the error in that particular module instead of going through the entire code base. Next one, alpha testing. It is the initial testing phase conducted by internal teams or users within the developing organization to assess the software, meaning the team that developed the software, before they launch it to the public, they do an alpha testing, meaning they test it out themselves. And of course, this is still not very effective because you know your code. You might not do something that will crash your program. And this is why developers also come up with another tool called beta testing. Most of you might be familiar with the Apple beta software program. So this is a software testing phase conducted by a select group of external users who assess the system performance. So what happened is that once you publish a software, you launch it to not everyone, but then a selected group of users who have signed up for this. For Apple program, I believe you need to sign up to just be the first one that tests out the new iOS system. But then the reason why Apple wants to do this is so that user can give it feedback on what went wrong. Okay, this is what it's stating here, beta testing. Last one, acceptance testing. It involves customers or end users verifying if the software meet their specified requirements and is ready for use or deployment. Meaning acceptance testing wants to test whether the software is accepted based on the user requirement here. Now, let's talk about test strategy. So there are many different testing methods. So which one should you use? That's when a test strategy comes in. It provides a structured roadmap outlining the goals, scope, methods, and resources for testing software, ensuring systematic and efficient quality assurance, defect detection, and software reliability. So how does the test plan look like? It ensures the expected sequence of operations within the software, verifies that the provided data meets specified criteria, validates accuracy of loop iterations, meaning that it ensures that there's no runtime error. It also ensures data is accurately stored in the intended location, validates the accuracy of the system outputs or outcomes. So there are a few ways to carry out this test. First way is using data. So there are different types of data that we have gone through just now. First one is normal data. Like what is the normal typical data that the program will receive? Abnormal, as implied by the name, like data that is not supposed to be input by the user. Boundary, meaning input value at the edges or extreme of valid ranges. It could be hard to understand using the definition. So this is why I create an example here. So let's say a program is written to get a number input from the user, and the input must be 1 to 100, and it must be an integer. So normal data would look like this, all the numbers that are within range. And normal data could look like this is a negative number, this is bigger than 100, and this is not an integer. To test out just how the system will react. And boundary data is basically the data at the boundary using 1, 0. So these are the boundary data because they are just at the edge of the accepted range, and 100, 101. So ways to prevent error, understanding the requirements, this is important. I believe this is the most important when you're developing a software. You don't want to create something that the user doesn't want to use, that the boss doesn't want you to do this. So you want to understand the requirement. Employing tried and tested design technique like structured programming and object-oriented design, which is something we'll talk about in the next few chapters. Utilizing conventions like the identifiers tables that we look at that the pseudocode chapter. They use proper data structure. And integrating tried and tested modules, meaning we only integrate modules or functions that have been tested into our main program so that we can reduce the probability of a program having an error. Now, we'll look into the last part of the video, which is the 3 different types of maintenance, which is pretty easy. Corrective maintenance. So once the software has been shipped, there usually needs to be maintenance usually needs to be done. And the first type is called corrective maintenance. It involves addressing and fixing software fault. Basically, if your program has a bug, then your role as a programmer is to maintain it by solving this bug so that it doesn't happen that frequent. So another one is adaptive maintenance. It adjusts program functionality in response to specification changes. So remember when I told you about the program development lifecycle, programmers will just keep going through the circle to add new requirement, new design, new code, new testing method. So one example for adaptive maintenance I see is how Facebook and Instagram evolve. So in the past, if you don't know, Facebook only have the post feature. And then when Snapchat comes in, they introduce this feature called the stories. And because it's so popular, Facebook and Instagram has to adapt, meaning they have to add features similar to what Snapchat do. So you can see that this is Facebook version of story and Instagram's version of the story. And look at how similar it is to Snapchat. So this is what we call adaptive maintenance, meaning adjust program functionality, add new features based on what the user wants. Perfective maintenance enhances and improves software by implementing additional feature, meaning you add stuff to your software to perfect it. One example is how YouTube added YouTube Shorts, so that it introduced a feature that allows users to create and watch short-form vertical videos. So this is not what YouTube does in the past, but because of TikTok, then it also add this feature to perfect the entire video software. And that's the end for this chapter. Hopefully you'll learn the process in which you create a software, and let me know in the comment section if you have anything that you want me to help you. And thank you so much for watching. I'll see you then.